right? We want to check how does the chair conformation looks like, and what does the flipping of the chair represent. These are the two important things we need to understand. Let me show you through video first how it looks like, and then I can explain you on the board, right? See that here. Okay, see, this is typically how the chair form looks like. Okay, like this. So you can clearly make out from here. If at all I annotate, I'm sure you can see that from here. One second. Yeah. So from here you can see this is how the chair form looks like. Got it? Second. So from here like this, and then it will go all the way like this. Okay. This is the way the chair form looks like. So I'm sure all of you got this. Now notice this one. These are the ones, if you notice, one, two, three. Here we have four. Then the one which he's holding, five and six. These are perpendicular to the plane which we are talking about, and actually upward and actually downward. So if you notice that these three are alternatively actually up, and these three are alternatively actually down. Okay, so that's how the cyclohexane conformer looks like, actually up and actually down. While, keeping that aside, if you notice the next six of them, these are the ones, one, two, three, and one more is on the back side, four, five, and six. These six are equatorially aligned. Okay, so that is the one thing you will notice. Now, have you noticed something that because of these actually groups, are almost on the same side, this pair of electrons, this pair of electrons, and this pair of electrons, they would have relatively more repulsions. They would have more repulsions. This is called transannular repulsion. All right, sorry, diaxial repulsion. 1, 3, 5. If you take the position, if this is carbon 1, then this will be 2, then this will be third carbon, then fourth carbon, then fifth carbon, then sixth carbon, like this. Okay, so that's how these are the 1, 3, 5, you know, uh, diaxial repulsions, or 1, 3 or 1, 5 diaxial repulsions. Got it? Now, due to this repulsion, and also there is a very, very small amount of strain here, very small amount of strain that you observe here. Got it? That strain, if you ignore, that strain, if you consider that strain and this small amount of repulsion here, that makes the ring to start moving across, up and down like this. And that's what I'm trying to show. Now, notice one thing, how it looks like. Got it? Check. Check it out. So this is how this structure has been present, and now, uh, right now you notice that in this case you can clearly see that where exactly he's holding this. This is the axial groups, right? And you can figure out where are the equatorial ones. This is the typical look, how it looks like while drawing. Got it? Right. So you can see this is the typical look what you will be making out of the drawing. Okay. Cyclohexane with axial bonds and equatorial bonds. Got it? Now, there is not ring flipping happening now, but it is being done. How? Watch this carefully. Got it? Just watch it carefully now. Okay. If possible, I'll make it little slower so that you guys can watch it much better. Check it out how it goes on this cyclohexane ring. If you notice, now this ring, he's trying to flip it up. Have you noticed something? The one which is going down, right, which was the chair form, it is like the bottom part is coming up, and now the part which was up, he's trying to put it at the bottom, like this. Okay, this is called the flipping of chair. Now what happened, if you notice the chair, this is the new form of the chair that you will notice. Got it? So this is the way it has happened, like this. Now this way, this is the new form of the chair. Okay, clear everybody? Right. Now notice the next part here. Now, whatever that were earlier axial, they all have become equatorial, and earlier, whichever they were equatorial, they all have become axial. That's the point we need to learn. Because if you may remember, all these black ones were actually equatorial earlier, and now they have become axial. Got it? Right? Okay. So you can see that if this is a group, clear, present on it, which are, one second. So see that group here, the group which is present here, correct? How it changes. Check out properly. The ball is at axial position first before the flipping, right? Before the flipping, it is at the axial position. Now notice the minute we flip it like this bottom and we bring it up, suddenly it has become equatorial. Got it? That's what exactly happens, guys. The minute it starts becoming a flip of a chair, everything which is axial becomes equatorial. Everything which was equatorial becomes axial. Got it? That's how the flipping of chair works. Clear now? I guess this part is understood. Right. Now, same thing. If it brings up, everything is changed again. Got it? So this is to release the strain. Everything which is axial will become equatorial, and the equatorial will start becoming axial. Okay? So I guess this logic is clear, everyone? Right. Now, let us understand the chair configuration, chair conformation. Chair conformation, the minute when you write it like this, after the flipping, it will become like this. That means the head will come onto the tail part and the tail will become the head part this way. Okay, that is how the flipping happens. Now you may notice that these are all the axial bonds. These hydrogens are all axially aligned, while these hydrogens are all equatorially aligned. Yeah. Now, if you go step by step, every step, right? Every step in that flipping, of course, that flipping happened very fast, quickly. But if you even pause that for very small instances and see how does the flipping actually occurs, this is what exactly happens. Notice, first the chair form, the minute you start bringing this head up, okay, bringing this head up here, clear? So before it can even reach upwards, first thing is it will almost come onto the same plane as this two. Okay, so this carbon 261 almost comes onto the same plane as that of 3 and 5 like this. Correct? That is like an intermediate stage. And that particular conformation is called as half chair. Half chair typically has huge amount of strain because this angle is also strainful angle. This angle is also very strainful angle for that. Okay. Then from this half chair, The minute you start pulling this up here, correct, then this group, because the axials has to come equatorial, equatorial has to become axial. So what happens, this carbon will suddenly face down and this carbon will suddenly face up. Sorry, this carbon will suddenly face up. So now let me relate that. This carbon and this carbon is same. This carbon and this carbon is same. Okay. That way, from the half chair, it will start twisting itself. Okay. Before it can make a complete flip of the chair, it will twist itself. And this particular conformation is called as twisted boat. And from the twisted boat, now you'll start working on the other side because I need to bring this down. So while you try to bring it down, now again these two carbon groups will come on the same plane. Okay, they will come on the same plane. And as you start trying to pull it down, again they'll start twisted the other way around. This time, while this was up and this was down, now this group will become down and this group will become up like this. So it will be reverse twisted. That's it. So chair, half chair, twisted board, then board. From board, again it will go to twisted board. From twisted board to half chair. And finally it reaches to this final chair, the flipped chair. So have you noticed one flip to make it, we have to go through three other new conformations. Okay. So one is a chair, half chair, twisted board, and board. These are the four different conformations. Just like how we had gauche, partially eclipsed, fully eclipsed, and anti in the case of butane, the same logic need to be applied here as well. Got it? Stability wise, if you notice, right, the chair obviously has the highest amount of stability. Then comes twisted board. Twisted board relatively has more stability as compared to that of boat and compared to that of half chair. Okay. Again, I can go through into a lot of details about how the twisted board looks like, what is its conformation, what is its Newman projection. Since we do not have all of that for J syllabus, I'm trying to skip it. When it is essential specifically for Olympiads, then I'll discuss it. But otherwise, it's not required. As much as J syllabus is concerned, very basic thing you need to know is what are the important conformations of cyclohexane, what is their stability order. That's it. So first one is being the chair form, then twisted board, board, and half chair. If such is the case, then if you compare the potential energy versus, correct, versus the flipping here, that flipping angle, flipping of chair is concerned, then you notice the most stable form is the chair form, isn't it? From the chair form, it has becoming half chair, which is most unstable form, isn't it? From here, it has becoming half chair. From half chair, it has becoming twisted boat. Twisted boat is relatively stable here. So this is like the twisted boat. From twisted boat, it has becoming boat. Again, it has becoming twisted boat. From twisted boat, again, it has becoming half chair like this. And from half chair, it has finally becoming chair. Correct? This is the way in which this particular group has been, I mean, the energy has been observed. Everyone clear? So you got to remember now how much is the amount of energy difference from here to here, right? If you compare that, this is around 11 kilo calories per mole. So that will be the strain energy in this case. Okay. This is what you will observe in the case of uh, cyclohexane cases. Okay. Any doubt here? Please do check. Usually, the flipping happens on its own at around room temperature. Okay. All the axial groups converts into equatorial and equatorial converts into axial whenever there is a ring flipping happening. This is what I told you, correct? If you, I mean, although it is not asked, just for the sake of information, I'm just showing it to you. This energy is approximately 23 kilojoules per mole, while this one is around 27 kilojoules per mole, right? And this total is this one, or approximately 45 kilojoules per mole. This is the energy diagrams. Okay, clear? Now, coming to the next aspect, that since all the axial are converted into equatorial and equatorial are converting into axial, does that mean every cis is converting into trans and trans is converting into cis? Answer is no, because cis and trans are geometrical isomers, and you remember geometrical isomers are only formed when there is actually breaking of bonds. Since we are not breaking any bonds, we are just bending it, we are just rotating it, these are only conformations. So cis remains cis, trans remains trans. Keep that in mind. Okay. Now, in case if at all I draw it in this structural form, you see, chair would be like this. This is the chair form here, correct? And after the flipping, how does it look like? Like this. This is after the flipping, correct? Clear? To showcase, how the axial becomes equatorial or equatorial becomes axial, let me just write down all the groups here. So these are all the original axial ones. These are all originally axial ones. Okay. These are all axial ones. And then these are all the equatorial ones. Sorry. Right. These are all the equatorial ones. Okay. After the flipping has done, let me give you the carbon numbers also for our understanding. This is 1, 2, 3, 4, 5, and 6. Right. Now, this carbon is now after the flipping this carbon. Got it? And the second carbon is this carbon now. Clear? That's how we need to look into it. So notice this. Now, whichever that were equatorially aligned, they all will be now axially aligned like this. So these are all axially aligned groups. These are the ones. Okay, and originally which were axial, now they all have become equatorial like this. Okay, sorry. Okay, these are all the equatorial ones. See the colors. Earlier it were axial. Now they all have become equatorial groups. Got it? Now you may have noticed that how do we need to emphasize which are cis and trans? Notice this one thing. Suppose if there is a group, some kind of a group here and another group is here, Now, what can I say? 1 and 2 are trans to each other because they are opposite to each other in their particular plane, isn't it? These two are trans to each other. If these two are trans, can I say, then these two, this group and this group, these two will be cis to each other, because on this position, if these two are trans, then the equatorial and axial has to be cis to each other. But now it's very difficult to say whether this equatorial and this equatorial are cis and trans. Adjacent carbons, if you compare, it's very difficult to say whether they are axial, trans configured, or they are cis configuration. So what you can do something, if you notice, these equatorial groups in this particular ring, in particular cyclohexane, we are not able to comment about their cis and trans activity. But the same 4 and 5 here, if you notice that they are actually trans to each other, isn't it? Those two are trans to each other. So although the same logic applies here, this one, equatorial and equatorial, in this case, we can't comment whether they are cis and trans. But those two groups here, if you notice in this particular conformation, in this chair, in this flipped chair, you can clearly notice that they are actually trans to each other. Got it? So always comment cis and trans on the basis of axial positions only, but either in the earlier ring or the original ring or in the flipped ring. Uh, Everybody clear? Now let me put the numbering for all of this. So it is 1, then 2, then 3, 4, 5, and 6. Hence, you can notice that during the ring flipping, geometrical identity of the group remains the same. That means cis remains cis, trans remains trans. Got it? Now that's what I need to showcase now, and we can make it a perfect table out of it. That when do we call something as cis and cis or trans and trans? Got it? Let me take this particular diagram as the reference, and from here I can clearly make out a table showcasing that the positions of the carbons and whether they are cis or trans. Okay, so you can see, taking that into reference, there will be, you know, groups. I can talk with respect to the groups. I can take with respect to the groups. Okay, and group is like this: 1 2, correct, 1 3, correct, 1 6, clear, 1 5, and 1 4. Okay, you can take one carbon as a reference. With respect to that, you can keep checking how the other groups are, aligned with it. Now notice one thing. If you notice 1 2 here, 1 and 2, their axial and axial are trans to each other. So let me put down trans. So you will find the trans isomer when both of these are axial and axial. And the logic not just only valid for 1 to 2, it is same as 1 to 6, because they are all both at equal distance. You can see if this and this group are opposite to each other, that means these are trans to each other. Correct. Same way, if these two are trans, that means the equatorial and equatorial also need to be trans. Correct. Why? Because after the flipping of the chair, these two will anyway become axial again. Therefore, an axial axial or an equatorial equatorial, both will make it cis form. Sorry, transform. While and axial equatorial or equatorial axial, these two will make a cis form. In these positions, 1 2 position or 1 6 position, if you consider one axial, one equatorial, that is actually cis form, or one equatorial axial, that means it is cis form. Now notice 1 and 3. 1 is here, 3 is here. So can you see this axial or on the same side? So I can say since they are same side, they are cis to each other. Correct? So which means I can say axial and equatorial. These two would be cis to each other in position 1, 1, 3 and 1, 5. Okay? Which contrarily can be said that an axial equatorial has to be trans and equatorial axial has to be trans. And lastly, again, when it is 1, 4, 1 and 4, you can see this group and this group. They are opposite to each other. That means that is trans. Therefore, an axial or equatorial is trans. An axial equatorial or equatorial axial is a cis form in 1, 4 positions. Okay. Please check this out. This is the important or main crux of this cyclohexane conformation. Okay. If anybody has a doubt, they will please ask me. I'll give you a minute's time. Please let. Now check this out. Given the geometrical isomers, right? Given these conformations, you're supposed to tell me whether they are trans or cis or which form they are. You can see this is equatorial and equatorial. Can you see it is like 1, 2 position? At 1, 2 position, equatorial and equatorial is what? Trans. So you can start answering for all of that. You can see this is a trans isomer, clear? And this is also a trans isomer. This is a cis isomer. This one is a cis isomer, right? This one is a trans isomer, clear? And this one is a trans isomer. This one is a cis isomer, right? This one is a cis isomer. This one is a trans isomer. Please do check if you all got that.
Sir,
Okay.
sir,
Right. Yes, Vita.
sir, could you explain the second last?
Yeah. Sure. This one, right?
Yes.
In this particular conformation, if you may notice, when you write the structure of it like this, then this way, this way, this way. This is the way you will get it, right, Beta? Can I say that this axial makes it trans? So in that case, the axial equatorial should make cis. That's the one which you. Okay,
Okay.
clear? Next. We did discuss about what is diaxial repulsion already, right? That is the van der Waals repulsions between the diaxial group decreases as the ring flip take place to the to take place them to equatorial position. Okay, that's the reason why whenever you have a bulky group around the axial positions, it becomes even more unstable. So we will always tend to keep the bulky group in the equatorial positions more than axial position. So stability wise, if a methyl group is positioned in the axial direction compared to that of equatorial direction, then equatorial itself will be more stable than axial, right? So this is the stability form. Likewise, if you have two methyl groups, right, on cyclohexane, then how we can align them and which of the four are more stable? Check it out. I can keep the two methyls axially up and down, equatorially aligned, or one axial, one equatorial, or one axial, one equatorial this way. Okay. Now, if you notice, in here, axial positions the more you keep it, less stable it becomes. So more equatorial you keep it, more stable it becomes. That means in the first equilibrium will drive more in the forward direction. Therefore, I can say the K1 is much greater than 1. While equatorial axial in this case would be almost equal to 1. Okay, because this is also cis, both of them will have similar type of repulsions here. And overall stability wise, if you notice that the most stable being the B1, then C and D are equally stable, then A is the least stable because both the methyl groups are aligned axially. Okay. Overall, if I tell you which one is more stable, I can say the trans form when it is equatorially is most stable than the cis form. Okay. I think the analysis is clear. So when you have two groups, you should be able to analyze like this and understand which one is the most stable form out of it. Clear? So coming to this point here now, check it out. If you have two methyl groups here, so as you align here like this and this way, this is K1 and this one, if you keep it both axially down, one, both equatorial like this, that will be transform. I mean, these two are cis, these two are trans. Okay. So you know that this is a trans form before flipping, this is after flipping. This is a cis form and cis form before and after flipping. Clearly, here one of them is axial, one of them is equatorial in the first case. So K1 will be almost equal to 1. While in the case of K2, it will be greater than 1. Okay. Stability wise, if you compare, definitely the D part is the most stable. Then A and B are equally stable, and C part is the least stable. Have you noticed? The cis itself is the most stable, and cis itself is the least stable in this case. Correct? So I can say cis, which is in the equatorial, is most stable, then trans, then cis, which is in the axial position. This is the stability order. Everyone clear with that? Likewise, if you have two methyl groups at 1 and 4 position, so I can align both axial, both equatorial, one axial, one equatorial, one axial, one axial, one equatorial this way. Again, same logic applies here. K1 is far greater than 1 in this case. K2 is almost equal to 1. And most stable will be B. Then C and D are equally stable. Then A is the least stable one. Overall stability, if you compare trans, let me put this terms. This is a trans before flipping, after flipping. This is cis and cis before and after flipping. So overall trans is more stable than cis. So trans, which is in the equatorial position, that is most stable as compared to that of cis form here. Okay. So here also you can notice the trans, which is in the equatorial, is the most stable. Trans, which is in the axial, is the least stable. Okay. And see, the magnitude of K equilibrium decides whether the flipping will be happening more frequently or less frequently, or it will not happen at all. Okay. For a cyclohexane, right? For a simple cyclohexane, if K is 1, right, in its flipping, and if I take this R group here, any R group here, once it is axial, once it is equatorial, and now I'm comparing this K equilibrium with your cyclohexane part, then relatively how much is the K equilibrium value? So check it out. When you have these two methyl groups here, then the K equilibrium value found to be 18, which shows that ring flipping is happening, but the tendency to remain in this side of the ring is more favorable. Okay, on the forward direction is more favorable. Likewise, when it is ethyl, it is around 23. That in that case also it will most likely to be in the forward direction. If it is fluorine 1.5, not very likely. Okay. So even if you keep it in the equatorial position, correct, not very likely fluorine can take place. Bromine 2.21. Okay. Iodine, you can see iodine is slightly lesser than bromine, correct? But that's okay, almost the same, that will not be compared. But very importantly, you will notice chlorine somehow has the highest value. Again, this is an experimental value, so you do remember between the halogens, chlorine has the highest, then bromine, iodine will be the similar one, and fluorine has the least amount. Okay, just a minute. Okay. So chlorine will have the highest value, then bromine, iodine will be the same values, and fluorine will be the least value. And have you noticed that as the alkyl group keeps increasing, there is a situation where when you have a tert butyl, the K equilibrium value is 4000, which means it will always stay in this position. This position it will not come, which means the flipping is almost locked. There is no more flipping observed. Got it? So this is why it is used as a blocking agent. If you do not want to make the chair flipping, then keep this group somewhere on the position. It will always stay on the equatorial direction and stop the flipping from happening. Okay. So check out this question now, how the questions are framed in this. Calculate the percentage amount of axial and equatorial of the following. What is the percentage amount of axial and equatorial in the following? Very simple. If axial is, originally it is 1, and out of that x amount has gone and x amount is present here, then I can say K equilibrium will be equal to x by 1 minus x into 100. Clear? So that would be equal to 18 percentage. Clear? Or you can write it as 18 by 100 also, doesn't matter. So as you solve it here, you will get this as x is 94.7%. Clear? 1 minus x, which is axial, is 5.3%. So this is the equatorial form. This is the axial form when you have methyl group. Okay. All of you understood this point? And now, if you were to write, because I have blocked it with this group now. Once I blocked it, you just have to write the most stable conformer for it. How does it look like? Okay. I want all of you to do it along with me. See, first write the cyclohexane part here, like this. So you write the cyclohexane part, then block it on the equatorial position here. Now, since this is equatorially locked, you need to think how these two are aligned first. Have you noticed, as per the given figure, these two are coming out of the plane, which means this is a cis molecule. And you know that at 1 and 3 position, when will you have cis? Because at 1 and 3 position, let's say these two, axial are cis, which means equatorial will also become cis. Hence, if I put methyl here, sorry, if I put methyl here, that will be the original structure for it. And this is the only form which we can write. Hence, it is the most stable conformation. Got it? Same logic in the next case. If you keep it like this and lock it here with the equatorial position. And then on fourth position, if you notice, this is coming out of the plane, this is going inside the plane, which refers it is a trans molecule. And axial are trans to each other in the case of 1,4 position. Hence, okay, sorry, equatorial and equatorial are trans to each other. Axial and axial are trans to each other in this case, isn't it? So therefore, here, how do we write down that? I can write it this way, this one, like this. So this is the correct structure. Ethyl. Here I have to write ethyl, here I have to write methyl. Next, here again lock it at one position. Okay, this is the way I have locked it. And now chlorine. Notice the chlorine part here now. At 1,3 position, this is 1 and this is third position. At 1,3 position, these two looks to be trans to each other. Trans. When do we put trans here? Equatorial and equatorial are trans. And equatorial because axial and axial are trans. Then equatorial and equatorial will also become trans to each other in this case. Got it? Sorry, I meant axial, equatorial are trans to each other in this case. And from the given structure, one is going inside, one is going outside. So therefore, if this is equatorially aligned, then the other group has to be axially aligned so that it is transformed. Got it? Because axial, equatorial makes it cis. So if it has to be trans, that means one has to be axial, the other one has to be equatorial. Next. Now, just now we have learned it that between chlorine and bromine, which can show more amount of annular repulsion, I mean axial repulsion, slightly chlorine shows more. So what you have to do, whichever gets more repulsion, that should be prioritized first. And you have to place that first thing in the equatorial position and then see about the other groups. So check out, if at all I keep, let's say, chlorine here, I would always prioritize chlorine. Let's say here I keep it and I keep it at axial equatorial position. Once you keep that, then you decide how the bromine is aligned to it. Yeah, because this is going in and this is coming out, which means they are trans to each other. And you know that if this equatorial is locked, then the other equatorial becomes trans. So this is the stable structure, most stable conformation. Likewise, if you have bromine and methyl, of course, methyl should be given more priority. So same logic, methyl you have to put it here and accordingly you can put the bromine here. Okay, next. Or did I delete something? One second. Try this one also. Suppose, by the way, these are all the ones which are given in, MS John book. Clear? These forms for practicing. Got it? So I'll recommend you what questions to do from MS John. So please make sure confirmation questions you attempt a lot of them from MS John. Check it out. If it has been given this way, so that means all of them are cis to each other, correct? And you know that in 135, cis position is all of them being trans or all of them being equatorial. Okay, I mean all of them being equatorial or all of them being axial. And since equatorial is most stable form, I can do it like this way. I can keep it this way, and here I can keep it this way, like this. So this is the correct structure. Likewise, if one of them I keep it like this and other two like this, in that case, first copy the structure and then we can align the other three groups here. So how does this look like now? So first this way, second this way, and the third one actually down like this. These three are the forms which you can write. Everybody clear with the stable conformations? Everyone? Right. See now, you have to write the stable conformation for this group now. So if you have to write the stable conformation, first you better write the chair form here. Okay. And Write down all the possible cases first, and then you decide what are the possible cases when you have two OH, because it hasn't been clearly mentioned whether they are axial or equatorial. You write both the cases and see. Got it? Now notice what are all both the cases means. Here I can have OH up, OH down axially. I can have OH and OH like this. Got it? Then I can have OH and OH like this. Got it? And I can have OH and OH like this. These are the four cases which you will get. Clear? See, here there is dual advantage. One, both both equatorial is always more stable, is what we learned. At the same time, have you noticed something? This is a particular conformation which is a gauche form. And in gauche form, due to hydrogen bonding, it is anyway going to be more stable. So if I put this as simple labeling A, B, C, D, I can clearly say that stability wise, B is going to be more stable than that of C and D, and the least stable will be A. Okay. So if the question is only asked whether the trans is more stable or cis is more stable, answer is trans. So trans is more stable than cis. Clear? Let's do the similar thing for the next one here. Okay. I'll just delete this case from here. Let me write it on the other side. Third position. So I can keep two OH here like this. I can keep one OH axially here and the other one equatorially, actually up, or I can keep both of them as uh, axial, equatorial to each other, or one could be actually up here and then, sorry, then equatorially here. These are all the four possibilities. Okay. Now notice one thing is for sure that usually this one has to be more stable because both of them are equatorial to each other. Equatorial to each other. But here is a very important catch we need to notice is that in this particular case here, when you write this chair form like this, here, when you have this oxygen and hydrogen like this bond, then oxygen and hydrogen bond like this, the chances are the lone pair present on oxygen will have a stronger attraction here with the delta positive charge. And that means even though both of them are axial to each other and they possess, okay, repulsions from here. Okay. So even though you have both of them axial to each other and they will have an axial repulsions, right? Yet you would notice that there is a hydrogen bonding which is established here. And because of this hydrogen bonding, clear, you would see that this axial hydrogen bonding will dominate over the other factors. Hence, stability wise, if you compare in such cases, you will have A being more stable than C, and then B and D least stable. Okay, everybody clear on this logic? Got it? Acha, I could keep it exactly the same structure, means OH and this attraction from this position exactly. Okay, to be more precise, just like the structure given. So let me write down that way here, like this. Yeah. Okay. Last one. In case if the two OH groups are 1,4 aligned to each other, right? If at all they are 1,4 aligned, in that case, how does it work? Let's see. If it is to be 1,4, what is the positions I can write? I can write this as OH here. I can make OH both equatorial. We can make one axial, one equatorial, or same logic, one axial, one equatorial, this way. Now, in such case, if you compare the stability here, you will notice that these two OH groups are anti to each other completely, which is trans, but these two are also trans to each other. And since both of them being equatorial, that B will be the most stable one. Then C and D will be next stable ones, and A is the least stable one. Okay. I guess this part is clear now. Now, here is the interesting catch, everyone. See, whatever the order we have written is correct. But does this mean the C and D part, does it exist in the first place? I mean, do you see that chair form will exist when you have two OH group? Answer is no, because you would see a new type of equilibrium established here. Basically, uh, when you have two OH groups here like this, you have OH here, and then we have uh, OH here, correct? So this is a transform, right? Now, instead of existing in this particular form, so what it will do, it will change its particular conformational identity into a board form. It will get into the board form. Got it? Sorry, this is not both trans. One is axial as well. Yeah, like this. Okay. Now, instead of staying in this form, it will start changing itself into board form. What is the advantage in board form? See, the same cis molecule, when you write it in the board form, you would notice like this. A lone pair of oxygen here can make a better attraction towards this hydrogen, correct? Since it is a boat, and in a boat, you know that these positions are called flagpole positions because that's where the flags we hang it around. So therefore, you would notice that there is a flagpole flagpole positions show hydrogen bonding, and that's why the K equilibrium will start, showing more factor, and board form is more stable. Conclusion here is, conclusion here is, right? In cis, you know, 1,4 diol cyclohexane, 1,4 diol cyclohexane, you will notice that the board conformation is more stable than the chair conformation. That's the logic you need to apply. Everyone clear? So it is only when you are analyzing about the cis form, that's when you have to use this logic. Clear, everybody? Right. To be honest, this is how much you need to learn it from the conformational analysis, everybody. Got it? So whatever we discussed in the last class, I mean, about geometrical and conformation, including today. So this is how much you need to know about these two parts of it. Okay. Now, let's get into more details about the uh, optical isomerism. Okay. That is the next point we need to discuss. One second. Today we'll do all the theoretical part of optical isomerism. Next class we'll do a lot of problem solving in this case. Okay. See, to understand optical isomerism, first we need to go back to the basics to understand the terms like what is symmetry, what are elements of symmetry, how is it valid in the case of how it is being useful in the cases of optical isomerism, and so on. Check it out. See, symmetry can be of many types, correct? A symmetry is based upon some kind of an event that happens around it, which suggests that, okay, there is some form of uniformity, correct? Likewise, you would notice that whenever we have symmetry, there are many elements of it. The first three, I mean, in physics as well as in chemistry, whenever we discuss about symmetry, we always analyze these three elements of symmetry. One is axis of symmetry, plane of symmetry, and center of symmetry. Along with that, there is one more symmetry part which we need to discuss, that is alternative axis of symmetry. When it comes to axis of symmetry, we are trying to emphasize on a particular axis within the molecule, where you rotate it will across that particular uh, axis, you should get some sort of symmetry. You should get some sort of symmetry. Let me analyze you with a very simple case. You can see the phone which I'm holding, right? Okay. So if this is more of a rectangular part, correct? So if you notice that if I take this as the axis, through this axis, if at all I rotate it like this will become 90 degrees. You will not see the same uniformity, or you will not see any kind of symmetry. But the minute I rotate by another 90 degrees, you will see almost the same type of nature. That means the distance, the amount of distance it will have, the kind of smoothness on this side, it will be similar, isn't it? Which means at every 180 degrees, there was a repeated pattern, which we noticed that there is some symmetry observed. So, how much is that angle that you're rotating? To get that similarity is what defines axis of symmetry. Suppose if you have structure something like cyclopropane, and when you are standing here to understand that, and then you are rotating, the cyclopropane is been rotating around here like this, you will notice first there is a CH2 group here, and the minute you rotate 120 degrees, after rotating 120 degrees, this B will come at this position. Again, you will see CH2. If you rotate another 120 degrees, you will see C will come at this position. So again, you will do check out CH2, correct? So that means the repeated pattern is observed at every 120-degree angle. Okay. Axis of symmetries are defined based on Cn factor. So n represent the number of times that you have to rotate to get the similarity. So 360 degrees divided by the angle. So how many times you have to rotate? Three times, correct? So that's why we call it as C3 axis of symmetry, or C3 if you have it, you also call it as threefold symmetry. Threefold symmetry. Okay. So I hope these terms are clear, everybody. Likewise, what if I take a cyclopropane and directly take it on the same plane of it? That means you're taking the same axis. The axis is touching C and also touching the midpoint of A and B like this. So if I take this as a plane, correct? It is like that kite, okay? More like a kite design on which there is a vertical stick present on it, and then you are just moving around. Or a flag, for example. If you have a triangular flag, and if at all you keep it at the center and you start moving this way. So in that case, if you notice you're standing here, you will see something like a screen here, correct? Cyclopropane screen. After rotating 180 degrees, again you'll get the same screen back. So you have to make a C2 axis of rotation for that symmetry to exhibit. Which means if I say a triangle or cyclopropane, these two are same. Shape-wise, these two are same. So they do hold C2 and C3 axis of symmetry. So total one C3 will exist and three C2 will exist, because C2 can be made like this, and like this. So total how many elements of symmetry we are noticing here? Four. Four different elements of symmetry, axis of symmetry which we are noticing here. Likewise, if you compare benzene, in the case of benzene, if I pass one axis through it, then I will have one C6 axis of symmetry. And if I take, planes like this, like this, like this, like this, and like this, again I'll get C2 axis of symmetry. How many C2 I can get? Six C2 axis of symmetries I can get. So only axis of symmetry, how many you are getting? Seven elements of axis of symmetry we are getting. Okay. I told you like this. N also represents the fold of symmetry. It is called n-fold symmetry. Notice methane. Now, when it comes to methane, methane is a tetrahedral structure here. So it will have a tetrahedral structure. If it is a tetrahedral structure, you notice that this hydrogen, hydrogen are on the same plane. They are on the on one particular plane like this, and the hydrogen is almost on the top of it, which will pass through the centroid of this triangle formed here, like this triangle which has been formed here, like this. So if I make that as an axis and then rotate it around, then I will get C3 axis of symmetry. C3 axis of symmetry. Likewise, if at all I pass it through this way and then rotate it around, I will get C3 axis of symmetry. Sorry, I will not get C2. I will only get C3. Like this, if at all I pass it, again I'll get one. Like this, if at all I pass. Like this, if at all I pass, I'll get one more. Like that, how many I'll get? I'll get four C3 axis of symmetries can be observed. That's what you notice in methane. Now, if one, two, three, four, these groups, either two of the groups are different, okay? If you have two of the groups different, then, okay, if two of the groups are different, then there is no axis of symmetry observed at all. Got it? So you would notice that in the case of tetrahedral. Next. What if you have cis type of a what if you have a C double bond C? In C double bond C, it is a planar molecule, right? It is planar, correct? In this planar, it is like a paper, okay? So it's like this paper. So you can see this is how the cis molecule, C double bond C would exist. So passing through the center of that here, then I can rotate it like this, correct? So that means I can get a C2 axis of symmetry, because if you're standing here, the same CH2 will be repeated after 180 degrees, correct? So you will have C2x in, 2y in y direction and x direction. Like this also you can get axis of symmetry. Like this also. See, if at all I keep it like this also, I will get an axis of symmetry. So you will get axis of symmetry in 2x, 2y, x, y, and z direction. So we got three C2 axis of symmetry in the case of a double bonded carbon. Okay. What if you have a trans kind of a molecule now, like this? If you have a trans kind of a molecule, correct? Can it show anything? Yes, it can, as long as it is in a z axis. Okay. Clear? Like this, passing through this one. And that means I'll rotate it like this. So this methyl will come all the way here and this methyl will come all the way here after 180 degrees. Therefore, it will have C2Z axis of symmetry. Got it? Likewise, if you notice here, this way, on this particular plane, if this is a plane, on the plane itself, if at all I put it like this, there is a plane of symmetry at 180 degrees, correct? And if at all I pass it through the center of it like this, through the center of it paper like this, then also I'll have one plane of symmetry. So I can have C2y and C2z axis of symmetry here. Got it? So these are axis of symmetry kinds. I mean, you can have many number of elements of symmetry like that, which are axis based. Next one is center of symmetry. As it comes to center of symmetry, what you need to notice is that they will have a same structure at opposite and equidistance from a point. Okay? Which means you have to decide a point on a molecule. From that point, if you go to any particular direction and you find some element here or some molecule here, some species here, the same species has to be repeated exactly in the opposite direction of the same distance, equidistance. At the equidistance, if the same molecule, same species is repeated, then that position, that point from where you started is called as the center of symmetry. Okay. B in such case will become, B in such case will become center of symmetry. Okay. For C and E point. Okay. Which are at equidistance and opposite to each other. Clear? Now, if C is equal to A, then B is center of symmetry. Okay. Which is also called, yeah, go it. Which is also called point of inversion. Okay. Another term used it is point of inversion. See, if you have a square, for instance, in the case of square, the center point will always, the centroid is always going to be the center of symmetry, because if you go this direction at some y distance, this direction in y distance, you will get the same type of molecule or whatever the feature that is present here. The same logic, if you go this side or this side, you'll get the same thing here as well. Got it? So that will become center of symmetry. Likewise, benzene will have center of symmetry. Now, pyridine does not have that center of symmetry, because if you go on this direction, you are getting CH2, but in the opposite direction, you are getting nitrogen. That means the center of symmetry can only be used, the terminology can be used when it is happening in all the directions. Which means here CH2, here CH2 is fine. Here CH2, here CH2 is fine. Here CH2 and here not CH2. That means it is not fine. It is not a center of symmetry. Okay. Similarly, here if you notice, from this point here, if I went all the way up, I got methyl, correct? And if this is the direction at which I go, correct? And if I go all the way down here, correct? Would I be getting this as a same methyl group here, correct? Sorry, I wrote it wrong here. One second. Uh, I needed to write methyls here. I forgot, because other could be same hydrogen. So I went methyl here and methyl here like this. If there are four methyls, two methyls are down here, one methyl is up and one methyl is down here. So problem here is this direction. I'm noticing that there is a point of inversion. But here, when I go down here, I get methyl. But when I go up here, I'm getting nothing. So it should always be in the inversion direction. So since it is not been able to see, that means this particular point is not a center of symmetry. But here it is happening. Notice from this end, if I go here, I get methyl. Exactly in the opposite direction, again I'll get methyl. From here, if at all I go up, I get hydrogen. If I go down, I get hydrogen. So therefore, that is center of symmetry as well. Okay. Likewise, here you can see the same thing. I have pictured it out. This is also not a center of symmetry. Okay. If you have a methane, especially if you have tetrahedral, any case, that will never have a center of symmetry. So tetrahedral will never give you center of symmetry. Remember. Now, when you have double bonded carbon, if you have these two groups same, then definitely there is a center of symmetry, because at inversion points you are seeing the same kind of molecule. In the cis form, you will not find center of symmetry, but in the trans form, you will be able to find the center of symmetry like this. So you can see here there is a center of symmetry. Okay. So remember, trans 2-butene has center of symmetry. Cis 2-butene does not have center of symmetry. The next one being plane of symmetry. Now, mirror images with this structure, by drawing a plane here, if you compare, then you will notice that how many plane of symmetries are present. Okay. See, suppose if you have a square here, clear, then I can make one plane here like this. I mean, I can make one plane which will cut this molecule into two equal pieces which look exactly same. Both the pieces will look exactly same, or they'll look like mirror images of each other. So you have to cut such kind of a planes which will make the molecule to look like mirror images of each other. I mean, after the breaking of that molecule. So here, when you cut it like this, it will be like this part and this part. Both will look exactly same. So that's why they are plane of symmetries. So this is one plane of symmetry. This is one plane of symmetry. This is one plane of symmetry, and this is one plane of symmetry. Okay. So you can notice that 1, 2, 3, 4, but the answer I've given it is 5. How come there are 5 plane of symmetries? Point is, whenever you have a square or a rectangle or something, correct? For example, if you have a square or a rectangle here like this, right? There is a internal plane, the self plane itself, which can also be used as a plane of symmetry. Because imagine like this is the paper, okay? I mean, these two are one particular molecule, but if at all I make like a sandwich out of that, so I cut between those two, so then also I can get one plane in between these two papers, isn't it? So therefore, a planar molecule by default will always have a plane of symmetry. So remember, every planar molecule does hold a default plane of symmetry. So that need to be counted as well. So total how many plane of symmetries? Total 5 plane of symmetries. Okay. Now, as it comes to benzene, one is a default plane. The other one is these six. One, two, right? Three, four, five, six. Total 7 plane of symmetries. In the case of methane, you can see in the case of methane, if I take this particular plane and cut it along, then this hydrogen and this hydrogen would be like mirror images of each other. Like that, I can take this plane and this plane, if at all I take, then these two hydrogens will become mirror images of each other. Likewise, if at all I take this particular plane here, then these two hydrogens will become mirror images of each other. Like that, how many plane of symmetries I can make? I can make such plane of symmetries. Okay. So for methane, how many total plane of symmetries we can have? 6 plane of symmetries we can have. Now what I'm trying to do, slowly in methane, I'm replacing one hydrogen by new element. So if I remove one hydrogen by chlorine, then obviously with chlorine, including this carbon, including this hydrogen, if at all I draw a plane, then I'm still getting a plane of symmetry here. Likewise, if I take this chlorine, okay, sorry, okay, if I take this chlorine hydrogen here like this, correct, and then I'm taking it as a plane of symmetry here, then also I'm getting that same kind of a feel here. Clear? I'm getting that plane of symmetry here. So in both the cases, I'll be able to, I mean, in this case also, I'll be able to see 1 and 2 and 3. Three such planes of symmetry I can get. Clear? We can get 3 such planes of symmetry. Okay. But now notice this one. Next, in case if you have CH2Cl2, okay, in case if you have CH2Cl2 here, sorry, yeah. In case if you have CH2Cl2 here, In that case, you have this carbon, carbon, hydrogen, carbon, hydrogen, hydrogen. This will make one plane of symmetry, which will divide these two chlorines. Next, this carbon, chlorine, and chlorine. This will make one such plane of symmetry, which will divide these two hydrogens. So total, how many plane of symmetry is only two. Finally, when you have a carbon with all four groups present, then there is no plane of symmetry. Okay. Now, such a tetrahedral position, such a tetrahedral center, right? Let me put down that a tetrahedral center with four different species on it is called chiral center. Okay, clear? So such a particular center is called as chiral center. Okay, notice in this case we learned that because it is by default there is one plane, here is one plane, here is one plane. So total there are three planes here. Here we can have one plane like this and one default plane. So we can have two. In this case, I can only have one plane, that is a default plane. There is no other plane of symmetry. A lot of students get confused, sir, ऐसा भी तो plane बन सकता है. देखो बेटा, यहाँ पे एक छोटा सा प्रॉब्लम है. When you take this as a plane, मिथाइल इधर है तो उसका मिरर इमेज इधर होना चाहिए. It cannot be at some farther angle. Got it? That's not a mirror image. So that keep that in mind. It should be perpendicular to, I mean, at the same position, perpendicular to each other. Correct? Then only we say it is mirror image. Clear? Hence, it has only one plane of symmetry. Got it? Now, what is an alternative axis of symmetry? See, when it comes to alternative axis of symmetry, first what you need to do, you have to rotate. Suppose I'll take with an example because alternative axis of symmetry is not observed in every cases. Okay, so you can be very example specific here. In this example, I have a chlorine here and chlorine here. Okay, and I took this axis and I rotated it around by 180 degrees. Then what would happen? Correct. This chlorine will come all the way here and this chlorine will go rotate and all the way here. So this is how it looks like, correct? So I rotated 180 degrees with respect to this plane, okay? This plane I have rotated, clear? Then the molecule which you got after 180 degrees, right? Then you take a perpendicular plane to it. So if you took this axis, now you take this perpendicular plane. That's why it is called alternative. Now this is the alternative axis and that plane, on that plane, you take a mirror image of it. If I take the mirror image of it, this is how the mirror image will look like. Now, if this mirror imaged molecule and the original molecule looks exactly same, that means the molecule possess alternative axis of symmetry. Everyone clear? So the axis to which we are rotating, then the molecule formed, then you have to make a perpendicular plane to this axis through which you have rotated. Just keep that in mind. That's okay. That will become alternative axis of symmetry. So here we had alternative axis of symmetry. Now same logic here also in this example also. This is the axis through which I have rotated 90 degrees. Acha, is it necessary to rotate always 180 degrees? No. Whatever angle you rotate, but in the axis on which you are rotated, the next plane through which you have to see should be always perpendicular. This time I rotate on only 90 degrees. So you see this methyl will go all the way up here. This methyl will go all the way up here. This methyl will go all the way up here. And this methyl will go all the way up here. Correct? So that's what exactly this looks like. Is that right, everybody? Now, once you get that, again I took the perpendicular plane here and then I take a mirror image of it. In mirror image, see whatever that is going down will appear like coming up, whichever is going up will appear like going down. That's how the mirror image works. And now you notice this structure and the original structure, they look exactly same. So therefore, what are these two? Since they are identical, that means this molecule possess alternative axis of symmetry. Okay. So that's how you need to judge about alternative axis of symmetry. Now, check out this very interesting analysis that there are cases where there are no plane of symmetry, no center of symmetry, but has an alternative axis of symmetry. Okay, there are some specific cases. Lot cases are not there. Yes, there are some specific cases where there is no plane of symmetry, no center of symmetry, but there are alternative axes of symmetry. The structure is little complex, but there are cases like that. That's why, remember, this is a very, very important statement question asked in JEE Advanced. Got it? That it is, right? If a molecule possesses no elements of symmetry, that means whatsoever, whether it is axis of symmetry, center of symmetry, plane of symmetry, alternative axis, कोई भी symmetry नहीं है, then only we call it as asymmetric molecule. We call that as asymmetric molecule. And if a molecule possesses axis of symmetry or alternative axis of symmetry, okay, but no center of symmetry and no center of symmetry and no plane of symmetry, then it is called disymmetric molecule. Okay, then it is called disymmetric molecule. And if all the elements of symmetry are observed, okay, here AAO is usually taken optional, but if all the other elements of symmetry are observed, that means the molecule is symmetrical. The molecule is symmetrical. Why it is taken as option is if all of them are same, there is no point of discussing alternative axis of symmetric only, because that will anyway be symmetric. Okay. And see, if a molecule is disymmetric with no alternative axis of symmetry, no center of symmetry, and no plane of symmetry, if these three should be absent, then the molecule is called chiral. Then the molecule is called as chiral. Chiral is a property, everybody. Chiral, chirality is a property. It is not some kind of a technical term. It is not some molecular formula or molecular name. Okay, clear? It is called chirality is some kind of a property of a molecule. See, if a molecule is asymmetric, it is always chiral. Asymmetric means it is always going to remain chiral. Now, what is chirality? A property of a molecule to have a non-superimposable mirror images. Such molecules are called chiral. Okay. So, for example, if I take this molecule A, B, C, D, a tetrahedral structure. In this tetrahedral structure, you know that there is no plane of symmetry, no center of symmetry, no alternative axis of symmetry, and no uh, uh, axis of symmetry also. Axis, center, plane, and alternative axis of symmetry. All four are absent. That means it is asymmetric. So for this asymmetric molecule, if I take a mirror image here, this is the mirror image which I'll get. Correct? Now what you can do is you try to rotate this mirror image here. I mean, you can just copy this mirror image here. Clear? Okay. And try to map with this molecule here. All right. You try to map onto this molecule here, like in any direction here. If you try to map it here, here in any direction like this, correct? You can rotate it around any direction. You can rotate like this. You can rotate here, here like this. You can make any such rotatory terms here and keep it moving. Then If it gets superimposed at all the positions, if it gets superimposed at all the positions, then those two are identical. Then those mirror images are identical. But if they are not able to superimpose, then they are called chiral. Got it? And the property to show this non-superimposability is what we call it as chirality. Okay. And what is interesting to notice is that when a molecule does not have any plane of symmetry, center of symmetry, and axis of symmetry, we are definitely certain that it will be a chiral molecule. Now notice, if an sp3 center, okay, tetrahedral geometry has four different groups on its molecule and it is chiral, and the center is called chiral center here, correct? Same way, a nitrogen having four different groups with a positive charge, that is also chiral. Because, like I said, it is only about the center. It is not necessarily carbon center. It could be any center. A tetrahedral center with four different groups. That's it. Okay. Next. If a molecule possesses only single chiral center, then the molecule is called chiral. Okay. If you have one chiral center, it is always going to be chiral. By default, it is always a chiral molecule. Clear? Now, when you have geometrical isomers, correct? Right? For example, if at all I have, you know, like this here, I have methyl and methyl, and like this, I have methyl and methyl, hydrogen and hydrogen. Now, notice when it comes to these two here, this would be trans molecule and this will be cis molecule. One is trans, the other one is cis, correct? What is the IUPAC name, everybody? So you can see it is 1, 2, 3, 4 but. So it is but2ene, isn't it? This is but2ene. Same way here or 2-butene. You can write it as 2-butene. Now this is also same name 2-butene. So to differentiate these two geometrical isomers, we use the terminology cis and trans. Actually, in IUPAC, the strict IUPAC, we do not use cis and trans. Rather, we use this as E and Z isomer. So we write it like this: Z2-butene or E2-butene. This is how we write. Correct? So E and Z configurations are used for geometrical isomers. Similarly, when it comes to optical isomers, or when it comes to chiral molecules, right, which are non-superimposable mirror images, then to represent them, we come across R and S configuration. We have been introduced with R and S configuration. Okay. Now, R and S can be assigned for each chiral center so that we can differentiate their IUPAC naming, first of all. And secondly, we should be able to see the varied properties within them. Check it out, how we can notice that this is a three-dimensional tetrahedral structure given. To write this three-dimensional, to assign this as R and S configuration, the easier method is first to adapt this molecule, which is three-dimensional, into a two-dimensional picture. It is like taking a photograph of it. So when you take a photograph of this particular molecule here, there is one important rule that we need to follow. Okay? Because when you are watching the molecule, you have to watch in that particular orientation such a way you should be able to see the molecule like this. So if you have a carbon here, we should be able to see that there are two groups which are going inside the plane and there are two groups which are coming outside the plane like this. So first you should be in the orientation or in the direction where the molecule looks like this. Okay, where this group and this group are going inside and this group or this group are coming outside. Then you take a photo of this one. Now when you take a photo of this one, suppose if at all I have A, B, C, D, And as you take the photo of this particular direction molecule in two-dimensional, how does it look like? You will have A, C, B, sorry, here it is C, D. Here. So it is D and here it is B. This is how it looks like, correct? Now, this type of a look of a two-dimensional figure is what we call it as Fisher projection. So Fisher projection in a way is also called as the top view of the molecule. So if I stand here and take the picture of this molecule, I should be making ensure that this hydrogen and chlorine are going away from the molecule, which means they are on the vertical line here, and this methyl and bromine are on the horizontal line. Okay, got it? So this is a very important rule that need to be followed. According to the Fisher projection, horizontally aligned group must be forward towards the viewer and vertically should be away from the viewer. Okay. So you can see here for this molecule, how do I need to watch it? Because I need it from the viewer's point of view. I will always need to look out from this end. So that this chlorine and ethyl should be towards you and methyl and hydrogen should be away from you. Same thing I have did it with this side also. Methyl and hydrogen are going away. Chlorine and ethyl are coming towards us. Okay. Now notice this one. When you are watching the molecule from this in this way, from this direction here. So this is how you are watching it. Okay. In such case, you will notice that this hand, the right hand would be towards chlorine and the left hand would be towards ethyl, isn't it? Because ethyl is coming out of the plane. So look at my direction here. If at all I watch the wall this way, okay, if at all I'm watching the wall on this direction, you can clearly notice that my left hand is, coming out of the plane, right? And my right hand is going inside the plane. Same way, here you can see the right hand is going inside the plane, the left hand is coming out of the plane. So the one which is coming out of the plane should be written on the left, one which is on the right hand should be written on the right. Okay, so this is not bromine, it is ethyl, Et. Clear now? And if a molecule with two chiral centers are given, okay, in case if you have two chiral centers, that means this is a carbon which has four different groups, and this is a carbon which has four different groups. So that means these two are the chiral centers. Then we already learned how to put the staggered configuration and eclipsed configuration. So in whatever way the molecule is given to you need to first convert into an eclipsed form. That's very important. So if it is in a staggered form, rotate it and convert that into an eclipsed form first. So you can see as I rotate 180 degrees, the groove which is present here will come at this side of the bottom. Then this group and this group will be on the same line. That makes it eclipsed. So this is how the molecule will become. So this molecule, when I rotate it by 180 degrees, this is what it becomes. Now once you get that here, right? Once you get that here, you decide whatever the head or toe is. Let's say this carbon is head, this carbon is tail. Okay. So then you take the molecule and keep it in front of you. Okay. Pointing head with head. Correct. Clear? Like this. In that case, now you would notice that with respect to this group here, this hydrogen is going inside, OH is coming outside, these two. Similarly, this OH is going inside and this hydrogen is coming outside. Now, when you watch the molecule from here, what I can say, as per the Fisher projection, the vertical group should be going away from you, which is what is happening. This methyl and methyl are going away from the viewer, and that should be placed on the up and bottom here, top and bottom here. And then this hydrogen and this OH should be on the right hand side, and this OH and this hydrogen should be on the left hand side. That's what we have written. So that's how you will get the Fisher projection. Okay, with this Fisher projection, everybody, any doubt here? Everyone, if you want, you can take some time, check it out. Any of the case, if you have a problem, you can ask me again. Since we got an idea about how do we write the Fisher projection, now it is about applying CIP rules and assign R and S configuration. Okay, so how do we assign that? Suppose if this is a chiral center in a Fisher projection, you have to apply the CIP rules, give the ranking system to all of them. So as per CIP rules, for this, with respect to this carbon, the first group connected is bromine, that is the high priority. So 1, then chlorine, 2, then methyl 3, then 4. And now you hide the fourth group and see how 1, 2, 3 are moving, in which direction they are moving. So here if you notice 1, 2, 3, they are moving in anti-clockwise direction. Okay. So here we'll put two rules. Check it out. If the lowest priority group is on a vertical line, if it is on a vertical line, then the clockwise rotation of the groups as to be assigned as R configuration center, R configured center. If lowest priority group is on the vertical line and anti-clockwise rotation of the group is observed, then it is assigned as S configuration. Then it is assigned as S configuration. Is that clear? So this would become S configuration. This is R configuration because here it is rotating clockwise and here it is rotating anti-clockwise. Okay, clear? I want you to just see how it goes away. So please check it out. In this case, this was the structure, how it is: hydrogen, chlorine, bromine, and methyl. The other structure was like this. This we learned it as S configured. Uh, I'm coming. And then we have chlorine here, methyl here, and bromine here. Correct? This I said it as R configured. Okay? I'm coming. So if you have noticed that if I put a plane, if I put a mirror across these two molecules, I mean between these two molecules, these two will look like mirror images of each other. Got it? These two will look like mirror images of each other. And that's what you are expecting as well. That means these two should be mirror images. Okay? And non-superimposable mirror images. Got it? So which means an R configuration and S configuration makes it, non-superimposable mirror images. Clear, everybody? Another way to look at it is if you want to, let's say, interconvert R to S or S to R. Okay. So here we have S configuration and I need to convert it to R configuration, or R configuration, I need to convert it to S configuration. Clear? What you can do, see, chlorine, if at all I exchange here with methyl, the one exchange which I do, that will give you this molecule. Okay. So how many number of molecules you have exchanged? Okay. This is called one exchange. So chlorine and methyl makes it one exchange here. Got it? 1 second. Just a minute, please. Yeah. So you can see here. Don't shake it. chlorine and methyl exchange has been happened here. This is called one exchange. So which means if you want to convert R to S, the number of exchanges required is only one or odd number of exchanges. So odd number of exchanges always lead to the change in configuration. Now, what if the lowest priority group is on horizontal line? Please check this example. Here, if you notice these four, priority wise, iodine will be first, then bromine, then comes phenyl, then comes methane, right? So if you notice one, two, three, these three are going with a clockwise direction. But the lowest priority is on the horizontal line. So now the rotation names will be different. See, if the lowest priority group is on the horizontal line, then the clockwise will become S configuration and the anti-clockwise will become R configuration. Okay, so you got to understand which case it will be R configuration and S configuration based upon the lowest priority being you know vertical line or on the horizontal line. Got it? And now check it out. When it comes to even odd exchanges, I told you already, if I exchange only one set here, that is called odd number of exchanges. So the configuration got changed. R has become S. If I take two exchanges, for example, B and D I exchanged and A and C also have exchanged, then this is the molecule. In that case, if this is on R configured, this will remain R configured only. Correct? So even number of exchanges will lead to the identical molecule. Odd number will lead to the non-superimposable mirror images. Okay? Everyone, please read out this note here. So important one, please do read the note here. If odd exchanges are performed, what would happen? If even exchanges are performed, what would happen? One. Done? Right. Now let us understand what is this optical activity of solutions. Okay. Imagine you took a solution which shows chirality. It shows a phenomenon of chirality, and I filled it in a test tube like this. Got it? Then what we are trying to do, we are taking a light, probably a white light. From there, we are letting it fall it on a nickel prism, and prism helps in separating out these rays, and you should be able to focus on only one particular wavelength. So that will become a monochromatic light, and all that light will be passed only in one direction. And if that light is passing only in one direction, we call it as plain polarized light. You might have seen the laser lights, like laser lights are the plain polarized lights, like that. If this light is let to pass through the solution, okay, and the light will transmit into the solution and it will come out of the solution. As it comes out of the solution, you have a angle reader here to read the angle of refraction from here. So as the light comes out of it, and if you see there is no change in the original angle, okay, so light went with the same vertical projection and it came as the same vertical projection, then we say the solution is optically inactive. Then we say the solution is optically inactive. On the other words, don't do that. The other words, in case if In case if on the reader you will see the light which went in this way has now started coming out in this way. That means with respect to vertical plane, it has made an angle of theta degrees. Correct? Or if it went this way, then with respect to plane, it made an angle of theta or phi, whatever the angle it is. Clear? Now notice if the solution is making any change in the angle, that is called optically active solution, whether it is on the clockwise direction or whether it is on the anti-clockwise direction. So if this direction the angle is increasing, or this direction the angle is being observed, we call the solution as dextro-rotatory solution. This solution is called as dextro-rotatory solution. While if it is making an angle on the anti-clockwise direction, we call it as levo-rotatory solution. Okay. And dextro-rotatory solution are called D solutions, small d, and levo-rotatory are L solutions, small l solutions. Okay. So what you need to understand from here, what is the summary of it? Check. Optically active solutions must rotate the plane polarized light. If they are not able to rotate, then they are optically inactive. Second, stereoisomers which rotate the plane polarized light are called optically active. If an isomer M rotates a plane polarized light in clockwise direction, it is called dextrorotatory. And most importantly, if one molecule is showing dextrorotatory, then its mirror image will show levorotatory with the same angle of rotation. Correct? So the non-superimposable mirror images rotates the plane polarized light in the anti-clockwise direction with the same angle. Now see, if 1 and 2 are non-superimposable mirror images, they are optically active and they are showing same rotation. In such case, we call 1 and 2 as enantiomers. So we say 1 and 2 are enantiomers of each other. Okay. Or 1 and 2 is also read as enantiomeric pair. See, any two stereoisomers which are non-mirror images, not optical isomers. Please remember it is stereoisomers. I'm using the term stereoisomers. Any two stereoisomers which are non-mirror images, then we call them as diastereomers. You know that geometrical isomer is also a stereoisomer. And in geometrical isomer, we can have cis and trans. And you know that cis and trans pretty well are not mirror images of each other. Hence, we can call 1 and 2 are diastereomers as well. That means cis and trans are diastereomers. Okay. Of course, they are optically inactive, but that doesn't matter. That is not what is the definition suggests. The definition is very simple. It has to be non-mirror images. That's it. As long as they are non-mirror images, right? And they are stereoisomers, then they are diastereomers. Okay. Here, if you notice this structure, this molecule and this molecule, they are not mirror images. You can see if at all I put mirror here, this side it is not matching. Here it is like a mirror image matching here, here it is fine. But at this location, it is not matching. Hence, these two are diastereomers of each other, which means this is optically active, this is optically active, but of not the same angle. These rotations are not same. Got it? Hence, these two are diastereomers as well. Now, another very important definition, last one. If molecule has multiple chiral centers, right? If you have more than one chiral centers, but it does possess a plane or a center of symmetry within the molecule, then such isomers are called as mesomers or mesoforms. Check this case. Suppose here there are two chiral centers, multiple chiral centers, and yet there is a plane of symmetry passing through this because this plane can divide this molecule and this molecule equally with the same features. So that is the plane of symmetry. Okay. And what happens here is when you have such plane of symmetry, if you take the mirror image of it, it is very easy to superimpose. You know how? You can just take this, clear, right? One second. We group it. Yeah, one second. Yeah. Now notice this one. What if I rotate it like this? That's it. You can see here, this is how the structure is. If at all I rotate it like this here, then you compare this molecule and this molecule. These two are exactly same. See, this one and this one are exactly same. So I didn't do anything. I just rotated. We didn't break any bonds only. Hence, when you have a mesoform, their mirror images are superimposable. Since they are superimposable, which means these two will be identical. So the mirror images of mesoform are always identical. Okay. And see, this chiral center will try to rotate the light in clockwise direction. Imagine. Then this chiral center will try to rotate the light in the anti-clockwise direction with the same magnitude. Hence, the overall effect on the solution, overall effect of the light is zero. That means there is no deflection observed. This type of cancellation of the light magnitude is called as the internal compensation. This is called internal compensation. Clear, everybody? So remember, the rotational operation, right, cancels off due to the opposite and the same magnitude of rotation, and this is called the internal compensation. I hope you guys understood these points.